Well, hi again, this is Bob, and we're getting ready to take a look at 7.1 over on the bottom of page 370. It's very important that you've read through this section here. A lot of this section refers back to what we learned in Chapter 6 about sample means, and you may recall the formula that they gave us. Just lost my pen there. You may recall in Chapter 6 we learned that the mean of the sample means turns out to be the population standard deviation, or excuse me, turns out to be the population mean. And we also learned that we have a correction on our formula for z-values when we're dealing with a sample. Remember, we first started off pulling one person out of a population and finding a corresponding z-value, and then putting a area and then percent probability with it. And the last thing that we learned was how to pull out instead of one person out of a population or distribution, we pull out 20 or 30 or several. So a lot of what we've learned here, what we're going to learn here, is based on things that we've seen in Chapter 6, and some of it even goes back to Chapter 3, where we were talking about the empirical distribution, how like 68% of the data values in a set or sample normally fall in within plus or minus one standard deviation of the mean, and how 95% of the data values from a sample or a distribution fall within 2 standard deviations of the mean. So we're basing a lot of the new stuff in this section on material that we saw in Chapter 6 and even back to Chapter 3. Anyway, we're going to learn about a confidence interval, and I've tried presenting this material before by the theory, and it seems to get bogged down. So I'm going to describe the situation and then give the formula and try to present the material from the formula, and along the way, hopefully we'll pick up the necessary theory. If nothing else, you will know the components of the formula and where they came from and how it's to be used. Anyway, they start off by talking about a college president wanting to know the average age of students attending the college. And I'm going to make the assumption that a really good poll was taken. It probably was not practical to get all the ages of all the students. So it looks like that there was a sample of 100. And we'll assume that that sample included classes throughout the day and the evening and throughout all the days of the week when classes were given. So when they did that, they got a sample mean of 22.3 years as the average age of students attending the college. And then they go on to tell us that this particular estimate based on a sample mean is called a point estimate. And they tell us that's a numerical value or estimate of a parameter. And remember, the idea in statistics is it's usually not possible to get the entire population, so we take samples from the population and then try to say that we have the parameter, the true value. In other words, what we're doing here is we're using the sample mean to arrive at the population mean. And we do that by samples, and we learned in Chapter 6 that the means of the sample means do turn out to be the population mean. Okay, and there were some other things that we ran across that I'll be making mention of here, but that's the idea. Samples, and from the samples we try to get an idea of the parameter, which in this case is the true age, if we were able to get all the students and find their ages and average them. Anyway, they go on to tell us that, they go on to tell us the next important thing. We have other measures of central tendency like median and mode, but they tell us that the best estimate of a population mean is the sample mean. Okay? Excuse me. And then the next thing that they tell us, again from the reading, which I'm sure or hope that you have done closely beforehand, is we don't really know, although I would say it's pretty good, but we don't really know how good our sample mean is. You may recall from chapter 6 that sample means, when you take all the sample means and find their mean, that's the same as the population mean, but that doesn't mean that the sample of 100 we pulled out is the best possible representation of the student body or the mean. So what they decide to do, and this is what this chapter is about, is to that 22.3 years, which we say is our sample mean, we're going to put a correction on it, and we're basically going to add some and subtract some from it, years. And we're going to do that, though, by using our standard normal distribution, or our z-tables, and taking advantage of some things we learned in previous sections. Okay, and when we do this, we're setting up what's called a confidence interval. And it's basically, it's something going to look something like this. We'll tighten up on it as we go along. We're going to believe that the true mean of the age of the college students is 22.3 years minus a value and 22.3 years plus a value. So we're going to, and actually we're going to add and subtract the same number to it, and the same number that we're going to get is by a confidence interval formula, which they show us over on page 372, about 2/3 of the way down. Okay, but hopefully we've at least laid out the situation where we have a sample mean, we have really no, due to the limitations of taking sample means, we're not sure that we've got the best sample mean, but we're going to put a correction on that sample mean based on our normal distribution, our z-tables, if you will, and by doing that, we're going to come up with a better answer. Okay, and so the next thing that they do is they give us two definitions at the bottom of page 371. They give us a confidence level, and then we actually have the confidence interval, which will be a mathematical interval. Well, I won't even bother with an example, but the first thing I want to do is talk about the confidence level. That is normally a probability, and we normally say I want to be 90% confident, in this case, that the true mean age of the students falls between this number and this number, or I want to be 95% confident that the true mean age of the college students falls between these two values, ages, if you will, in years, or I want to be 99% confident. Okay, and of course, once we choose a confidence level, we're going to use values from the z-tables here to find the confidence interval. So, but the first thing we normally do is we select how confident you want to be that the true mean is in between the two values in the interval. So this is right off the bottom of page 371. And what I want to do now is just go look at this new formula that they're going to give us, and then I want to explain the idea of confidence intervals and alpha, and a little bit about where this formula comes from. And then I thought we'd just go work an example, and we can use working through the example to help understand the formula and the theory behind it. So here is the confidence interval formula we're going to use. It's got the sample mean, and to the sample mean we're going to add the product of z sub alpha over 2, which I'm going to talk about in length in just a second, times the given standard deviation, which we know in this section, divided by the root of the sample size. And notice on the other side of our mean, we're going to have our sample mean minus z sub alpha over 2 times the standard deviation over root n. And it turns out the answer we get on the right side here, or I should say the answer that we get from z sub alpha over 2 times the standard deviation divided by root n, this amount that we're going to add to the sample mean will be the exact same amount that we're going to subtract from the sample mean. Okay, but so let's see what we already know here. We already know that U is the population mean, and that it's going to lie between two values. And one of the values is the sample mean plus a specific number, let's say like 2. In other words, we're going to add 2 to the sample mean. And on the other side, this side here, we're going to say, for example, subtract 2 from the sample mean. So it's going to give us a range of values in which we firmly believe, let's say we're 99% confident that the true population mean or the population mean lies. Anyway, we know what this is. This is called the sample mean, and that will be given to us. And we also know that the z sub alpha over 2, which I'm going to explain in just a second, that ties in with our z-tables. Now, this should look familiar from the standard deviation divided by root n, and that z sub alpha over 2 are all related, and they tell us, in fact, that toward the bottom of page 272, they tell us that z sub alpha over 2 times the standard deviation divided by root n is our margin of error. Okay, and this is the correction that we're going to use to add a little bit to the sample mean and subtract a little bit from the sample mean. Okay, and they tell us the margin of error is also called the maximum error of the estimate, and it's the likely difference between our point estimate, our sample mean, and the point estimate of a parameter and the actual value of the parameter. Now, if you want to know where the whole derivation of this formula comes from, and it's really not that hard to follow, it's over on page 378. And when I say the formula, I mean the one that I wrote up on top here. But the only thing that I haven't really discussed yet is the z sub alpha over 2. Okay, and I hope this isn't too messy, but I'm sure that after trying to explain this 2 or 3 ways, one of them will make more sense. They're all pretty straightforward, but z sub alpha over 2 refers, first of all, we need to know what this alpha is, and the alpha is the area in the 2 tails of our distribution, of our normal distribution. Okay, so here's our normal distribution, and of course these are the tails. Now, we know, for example, that most of the area in the bell curve lies in the hump of the bell, if you will, and the area rapidly diminishes when we get into the tails. Okay, so what we're dealing with now is two tails, and we want to come up, we need some values for this z sub alpha over 2. And if I'm just going to give you the examples here because there's a complementary relationship between the alpha and the confidence intervals. Remember when we had a confidence interval, let's say of 90%, well, that leaves 1 minus 0.90 or 0.10 or 10% of the graph, if you like, in the tails. In other words, 90% of the graph would be in the middle or the hump of the bell, and then the other 10% of the graph would be in the tails. So if we have a 90% in the hump, that leaves 10% to be divided between the two tails. So the 10% is called the alpha, the Greek letter alpha, and then alpha over 2 would equal 0.10 divided by 2, or 0.05. And so what we would really end up with, and I'm going to keep doing this for all possible values, is when we say that alpha equals 0.10, that also means that we're dealing with the 90% confidence interval. In other words, this would be the area in which our sample means fall in, and then we've got another area here in the tails, and there's two tails. Remember, we can be on either side of our parameter there, in this case the sample mean, and to find out the area in each of those tails, we take the alpha, which is 0.10, and we divide it by 2, so alpha over 2 equals 0.05. So 90% of the area where our sample means will fall in is in the hump of the bell curve there, and the other 5% is represented in each tail for a total of 100%. So let's say that somebody said, well, I want you to use I want to be 95% confident that the true mean falls, I want to set up a confidence interval that I want to be 95% confident of the interval in which the true mean lies. Okay, well, this is what 95% confidence interval would look like. Here's the area in which of our sample means would fall in, and then we've got two other areas to take care of there. Okay, and if we have a confidence level of 95%, then we would go 1 minus 0.95, that's 95% as a decimal, and that would give us 0.05, and that would equal our alpha. So saying an alpha of 0.05 and the 95% confidence level are the exact same thing. Okay, so 0.05 equals our alpha, of course, so alpha over 2, to find out the area in each tail, would be 0.05 over 2, or 0.025. So when we're dealing with the 95th confidence interval, or I should say the 95th, when we want to be 95% confident that like in this case of the true mean age, we would have 95% of the sample means falling in the hump of the bell there, and it would leave 0.025 on the other side. And by the way, the 0.025 is our z sub alpha over 2 value. And then we would have to go find that, and it turns out this is used all the time. It's just 1.96. And I'll talk a little bit about that as we go along also, because I'm going to summarize every bit of this as when we get this last one done. Now, what about if we had we wanted the 99th confidence interval? We wanted to be 99% confident of where our true mean lies. Okay, well, we would go 1.99, and that would give us 0.01, and that is our alpha. Okay, that's the area that will be cut into the two tails. So to find alpha, so the 99% confidence interval or level is the same as alpha of 0.01, and then the amount of area in each of those tails would be 0.01 divided by 2, or 0.01 divided by 2. I don't know why I can't think too good today, but that would be, I have to grab my calculator. I can't believe I'm so wrapped up in this that I should be 0.005, excuse me. I'm just thinking too much about the theory here. So 0.01 divided by 2 is 0.005. Okay, so our situation would be this. Each of the tails would have 0.005 in terms of area, and 99% of the graph, or our distribution of our sample means, would fall on the outside. In other words, they'd be in the middle of the bell there, and then at the extreme parts in the tails would be the other 1%, cut in half. Okay, so let's summarize some things here. Let's first do this. Let's set up for a confidence level, and then we'll set up for a alpha, and then we'll set up for our z sub alpha over 2 values. And when our confidence level is the 90, we want to be 90% confident, our alpha is 0.10, and of course our when we cut that 0.10 in half for our alpha over 2, we get 0.05, and the z sub alpha over 2 value associated with that is 1.65. Okay, and we would get that by finding an area. Actually, I can draw a little sketch of the area that we would be finding. We would be going from the tables to the z value. Okay, so we'd have like 0.05 in each of the tails, and we'd have 90% here. And what we would do is, if you noticed, we would have like from this line right here, this is our z value we're looking for, 95% of the graph is to the left of it, and we would go into our tables and we would find the value 1.65, and that's our z sub alpha over 2. Okay, well, when we were talking about when we wanted to be 95% confident, that gave us an alpha of 0.05, and when we cut alpha in half, we got 0.025, and it turns out that its value is associated with 1.96. So you don't have to keep looking these up each time. In fact, they tell us both on page 372 reviews what I'm doing, and somewhere back on well, when I find it, I'll make reference to it, but it's used in the sample questions also. Anyway, our last one, when we want to be 99% confident, that left us an alpha of 0.01, and when we cut that in half, we got 0.005, and its z sub alpha over 2 value is 2.58. Okay. Well, I think we've got enough I'm going to write the formula again. And on the left side, All right. So we know the situation. We hopefully know what the z sub alpha over 2 is. It's just a z value, and we're going to use that same z value on both sides of the interval. We're going to be given a standard deviation, and we're going to be given a number that was sampled. So what we're going to try to find out is we're going to establish the interval for a given confidence level. And I'm going to work a couple of questions. I think what I'm going to do is work the first example question, example 7.1. Just hope don't lose my computer or my internet signal here. And then we'll come back and I'll do the rest of the section. But at least we'll have this to build on. And it talks about the days it takes to sell a Chevy Aveo. And it turns out a researcher wants to estimate, this is on page 373, by the way, the number of days it takes an automobile dealer to sell a Chevy Aveo. A random sample of 50 cars. Okay, here's the first thing we need. So they sampled 50 cars. That's a pretty good sample size. Had a mean time on the dealer's lot of 54 days. That's our sample mean. Now, remember that sample means can vary. We know the mean of the sample mean is equal to the population mean, but we know due to sampling error that that particular point estimate may not be as good as we think it is, so we need to put a correction on it, and we're going to put a correction on it by using the formula that they've given us. The next thing that they tell us is that the standard deviation is known to be 6 days, actually 6.0 days. So we want to be 95% confident of the interval of the population mean. That's for the number of days. So our confidence level is equal to 0.95 or 95%. Now, you don't need to go through this again, but I'd like you to look down at where they worked the question out and notice that they use 1.96. Anytime you're dealing with this type of situation and we have a confidence interval of 95%, that's immediately like saying, well, that's alpha of 0.05, and that would be like a z alpha over 2, or alpha over 2, of 0.025, and then you would go to the graph, our standard normal distribution tables, and you would always find that the z value associated with that, in other words, we'd have 0.9, you'd have 0.95 of the graph in the hump of the bell, and you'd have 0.025 in each of the tails. And in the tables, you would look for the closest value of 0.95 and 0.025, which would be everything to the left of 0.9750. But we have another example that we can deal with that when I do part 2 of this lesson. Anyway, we have, and so the last thing I'm going to write is our z sub alpha over 2 value is equal to 1.96. We don't bother with the negative one. We only put the positive one in the formula. So I'm going to set this up. Our sample mean of 54 days plus our 1.96, that's our z sub alpha over 2. That gets multiplied times our standard deviation of 6 days, and that gets divided by the root of the sample, which is 50. And on the other side, we have our 54 days minus 1.96 times 6.0 divided by root 50. Now, you have to come up with a way on your calculator, and everybody might have, or everybody doesn't have the same calculator, that you can consistently come up with the same answer as the book. Please don't assume that just because you can set it up means that you can solve it. Because what we're going to get is just a little bit of a correction on each side of our sample mean. In fact, the answer is that the true mean lies between 55.7 days and 52.3 days. So notice we went from 54 to 55.7. We added 1.5 days, and we went from 54 to 52.3. We subtracted 1.7 days, excuse me. So another way to write this would be 54, although this is the preferred way, but we could also say 54 plus or minus 1.7 day. Okay, but this, the way that I've written it in interval notation, is the preferred way. So I'm going to close off this section by asking you to, before I come back, make sure you know where the 54 came from, make sure you know where the 1.96 came from, the 6.0 and the root 50, and make sure that you can come up with the same answer that the book did. Okay? So I will be back shortly with the second part of this lesson. I'll do a couple more example questions and try to fill in a little more theory. And in case you're wondering about the z sub alpha over 2, they give us a problem using the 98th, if we wanted to be 98% sure of where our population mean was. We don't normally use this interval, but I can clean up a little bit or maybe do a extra explanation on how we get the z sub alpha over 2 values. Although, as I mentioned, we keep using the same ones over and over again. Anyway, I'll be back shortly. Thank you.